It's 2, so I guess we can start. First, I would like to ask you to close your mic if possible during the webinar in order to facilitate the recording. So welcome everyone to EURASIP webinars. First, I'm going to say a few words about this regular webinar that take place almost every month. So the webinars cover the whole range of topics of EURASIP, going from audio processing to image analysis, but also communication and so on. Each webinars aim to cover a specific topic in a wide range of signal processing, but the goal is to be accessible to the whole audience of EURASIP. So I can just encourage you to have also a look on the other EURASIP webinar. So there is a YouTube channel where you can find the previous webinar. And you should receive also, if you are a EURASIP member, newsletter with the information of future webinar and also a specific email dedicated to webinars. So do not hesitate to participate to the future one. So now it's time to introduce our today's speaker, who is Professor Ulugbek Kamilov. He defended his PhD 10 years ago in Switzerland at the École Polytechnique Fédérale de Lausanne. Then during 2 years, he was a research scientist for Mitsubishi Electric Research Laboratories. And since 2017, he is associate professor of Washington University in St. Louis and director of Computational Imaging Group. So he received many awards, so both for his research, but also for teaching activities. So I'm going to cite a few of them, so such as the NSF Career Award, the Outstanding Teaching Award from the EC Department of Washington University, and more recently he received the IEEE Signal Processing Society Pierre-Simon Laplace Early Career Technical Achievement Award. And for the most recent one, you also have the Donald Schneider Career Development Professorship at Washington University. In terms of research, his research focused both on fundamental and mathematical aspects of imaging, going from large-scale optimization and mathematical tools for computational imaging, and also application-oriented projects, mainly in medicine and biology. So you probably know, for most of you, that he recently was pioneer on plug-and-play strategy for image reconstruction. And his talk of today about implicit prior will be for sure very inspiring for all of us. So I'm very pleased to welcome him for this webinar. Thanks a lot to you, Ulugbek, to accept this invitation, and the floor is yours.
Thank you so much, Nelly, for this very generous and nice introduction as well. Thank you so much for having me on this webinar. It's really a pleasure to speak about some of the more recent research I've been doing. I did try to focus on one topic, although I had a hard time to pick a topic I wanted to talk about, because there are a few things I wanted to share with people about this whole theme of using restoration deep networks for regularizing imaging inverse problems. It is funny that today it's 2025. So as Nelly said, it's been 10 years since I finished PhD, so time really flies. But I really have been enjoying doing research. So my research really focuses on computational imaging, and in particular within the computational imaging, which basically is a subfield that tries to integrate image acquisition with image reconstruction in a way that can reduce the weight on hardware by pushing it to software to imaging inverse problems, right? So imaging inverse problems, I'm sure a lot of you are very familiar with it. For those who are not, and for the sake of introducing the notations, what I'm really interested to talk about today is recovery of some unknown image X. So this X here is unknown image. You can see it's a 3D algae. It's from microscopy. Unfortunately, the reality is we cannot see directly, so we observe it through some sensors. And in this case, it's intensity diffraction tomography, so optical tomographic microscope that basically gets us sets of projections optically from different angles, right? And you can see my notation here is basically what I observe is y, which is my measurement, and that y is related to unknown image through this forward model, this measurement operator. And notation, I'm going to use this a, and usually there is this little phi here, which might denote that there's some uncertainty or some parameters that I don't know exactly in the measurement model that might need to be calibrated as well. In addition to the measurement model, which, by the way, can lead to information loss because we might not be able to observe everything about X directly through the sensing system. There's usually also a modeled noise, which is, this injection of noise, which we usually model as a random quantity. And I'm going to talk to you about it today. So the language usually is used in the field is, we say, forward problem is this actual physical process of going from X to Y. This is done by the device. This is how we obtain the measurements. And usually we know this A up to those parameters phi. And what I'm interested in is inverse problem, which is basically, okay, now I have Y, let me go back to X, right? So this area has been explored for hundreds of years. It's a very active research area, has been reinvented, re-injected with new ideas over many, many years. But the reason I really like working in this topic is just because so many problems in real world can be modeled using the same mathematical notation. So this fundamental problem, Y equals AX plus noise, can go from all the way to bioimaging, which could be microscopy, medical imaging, CT, MRI. You can think of scientific imaging, for example, Raman microscopy, or you can even think photography nowadays is image restoration in computational photography is often also based on solving an inverse problem where we observe some image Y or typically image sequence, and we want to recover the high quality image X. All right. And it's not secret that deep learning really transformed the way we do inverse problems. If you think about it, we just mentioned a second ago that I did my PhD thesis 10 years ago, so 2015, which has been a while, but not really crazy while if you think about it. But when I was doing PhD, this type of block in painting was unimaginable to do, right? So trying to go from observation of this form to reconstruction, so quote unquote reconstruction of this form was pretty crazy. But this is something we can routinely do nowadays by using very strong priors on missing information to try to predict the plausible look of the missing regions. And this figure is in fact from one of the papers I'll mention at the end of the talk, which will be presented by my collaborator, Matthew Terris, at CVPR 2025 right now, right? All right, so how do we approach typically imaging inverse problems? So there are many approaches over the years. Of course, I cannot make justice to all of them, but the ones I've been heavily focused on are based on trying to come up with a statistical model to try to solve them, right? So as I mentioned, we know the forward model. So the unknowns here are X, and usually we don't know the noise. So the statistical modeling says, well, I'm going to say something about the noise. We assume that noise follows some kind of statistical distribution. So while we don't know it, it comes from some known statistical family. So I'm putting Gaussian because I'm going to use a lot of least squares. But you could imagine generalizing it to Poisson and other types of noise models people commonly use. But the key here is the fact is we need to assume something on X, so unknown image. So measurements by themselves in inverse problems cannot fully describe the unknown image. So the whole art of imaging inverse problems, just like you saw in a block in painting case, is trying to restrict possible solutions X such that given Y, I can predict X. And one common way is to say, you know what, I'm going to assume that X comes from some statistical distribution. And in the case of imaging, that statistical distribution has properties of living in a lower dimensional manifold, right? So I'm using this term not mathematically, I'm using it very loosely. The reason is like the way I'm trying to go about it is being just very pragmatic. We know images are compressible. This has been the premise of my research since the era of sparse representations. We could represent images in a very compactly over wavelet domain and so on, which basically suggests that image prior is generally lives in a lower dimensional space than the dimensionality, intrinsic dimensionality of n. So if n is an n-dimensional vector, so I'm talking about discrete case, px is going to be some manifold in that n-dimensional space, right? So the whole art is trying to coming up with px so we can try to solve. If I did know exactly the prior, now I could do a lot of interesting things. So one common thing in the literature has been to say, okay, I can design a map estimator, right? Or I can design another type of statistical estimator, for example, MMSE estimator. So in the case of map estimator, I can say, well, I have a Gaussian noise, I put the least squares, and what I'm going to put as a regularizer or as a prior to restrict my possible solutions, because this term by itself doesn't fully describe the image X, I'm going to add the negative log of the prior, right? So basically here now I'm trying to maximize probability, so a posteriori probability of X conditioned on Y. So this is a very common approach done in literature. But okay, it does assume that we know the prior PX, right? So now, how do we actually design this type of regularizers? So there have been few approaches over the years. Of course, the classical one, when I was still doing PhD, was transform domain sparsity, which would say, well, we assume that X is sparse in some kind of transform domain. So this was a pre-deep learning priors. Typically would put some L1 norm or LP norm and try to minimize it. So very popular total variation regularization is based on this idea. Then another common approach is to use deep learning, and very common way of doing it has been deep unfolding or deep equilibrium models, where we basically say, you know what we're going to do? We're going to try to design H. So we're going to do it implicitly, right? How are we going to do it? We're going to try to write out this minimization problem that we have here. So for the map problem, I'm going to write the iterations of that algorithm. So it could be gradient descent, proximal gradient descent, ADMM, any algorithm you like. I'm going to unfold it into certain number of iterations. And then I'm going to say whatever comes out of that algorithm, so my X hat, should be close to the ground truth X. And I'm going to train that thing end to end. So this has been extremely successful and broadly used. Probably some of the state-of-the-art algorithms in many image reconstruction problems were based on the deep unfolding. And even now, if your goal is to do MMSE performance or performance for some specific metric, deep unfolding and deep equilibrium models stay as very, very competitive in terms of performance. And finally, the third approach, which is going to be much closer in the spirit to what I'm going to talk about, is the approach based on plug and play or score-based models. So when I put score-based models, this implies or relates to diffusion models because they're based on a very similar principle, is that we can say, I'm going to try to learn the prior that's going to be implicitly learned by denoising images, right? So the way we're going to do it, we're going to take an image X, so a bunch of images, add additive white Gaussian noise. Nowadays, for different levels of sigma, we're going to train that model. And the H that's going to be learned from that for a given sigma will be Px convolved with a Gaussian kernel G sigma, right? So that's going to log. So that's going to be the prior in that sense. And now we can leverage the Tweedy's formula that says the gradient of this H would simply be X minus the denoisers that we trained, scaled by the noise level, right? So this has been a very common way of doing. So you can see the evolution of different approaches of used in variable and then differences between them, all right? So today I don't want to talk about none of these three approaches. In fact, I want to try to bring another perspective for designing priors. So I don't want to do denoising, but I want to talk about more general restoration operators and trying to define the regularizer implicitly through restoration operators. So this is a line of work that goes back to 5 years. So I've been working on this related area over 5 years. So this gives me some chance to highlight potential benefits of designing priors in this way or using off-the-shelf restoration network as priors. I want to just highlight some of the collaborators here that I'm going to present those papers. So the first one was done with my students and Professor Hong Yuan. The two subsequent papers that you see here, so the restoration network as implicit prior and stochastic deep restoration priors were done with team at Google, Peyman, Milan, Far, Maurizio, as well as my students. And finally, the last one was a collaboration when I did my sabbatical in France last year. I got to collaborate with Mathieu Terres and Thomas Moreau together to do another interesting extension of using restoration priors in a new way. All right, so let me give you this perspective. So basically the insight I want to throw in here is that if you look at restoration degradation prior composition, right? So I take the image, I degrade it by adding some measurement operator or some kind of blurring operator, some degradation H, and I add noise to it and I restore it, right? I get this composite operator that goes from X to X versus naive fixed point, right? If I take X and I simply plug into restoration operator, then if you can see, if I iterate on this to try to find the fixed points, on the right-hand side, I have composition of restoration degradation. On the left-hand side, I just have a fixed point of the restoration operator. You can clearly see that images are not fixed points of just restoration operators. However, they are near fixed points of composition of degradation restoration operator. So here, this is done, the simulation was done by Mathieu on a SkuNet for JPEG restoration algorithm, but you can do also for restformer for Gaussian deblur. So again, I can just look at the fixed point, which is naive fixed point of just running, iteratively restoring this image, or looking at a pair of degradation restoration. You can see here, the image is much closer to natural images. So the claim I want to kind of bring forward is maybe this observation that by degrading and restoring images can give us a nice formulation for using this type of models like SkuNet and restformers that have been pre-trained already as priors for regularizing inverse problem, right? And trying to come up with ways to justify this approach and try to design algorithms based off this idea, right? And that's going to be the focus of this talk. And another interesting perspective here, we don't even have to be restricted to one type of degradation restoration. For example, I could take, JPEG restoration so both SkuNet for Gaussian deblur and then JPEG restoration, I can call them R1 and R2, and I can look at the fixed points of degradations and restorations by sampling or by the averaging over all kinds of restoration and degradations, right? I could take an image, degrade it 100 ways, restore each one of those and average the solutions, right? So, and then looking at these fixed points, and generally these fixed points, linear combination of multiple restoration degradation operators will lead to improved fixed points. And my claim is this will bring us even closer to the imaging manifold. All right, so that's going to be the main point. And the rest of my talk essentially is going to be trying to bring some more concrete framework around this idea of using degradation restoration pairs. All right, so let me start by just introducing the premise of this. And this comes from the iClear paper from 2024, a restoration network as an implicit prior. So what we want to look at is networks, so R theta star here, which takes some kind of degraded image to a restored image, right? So you can see my degradation S equals HX, right? I observe S, which is both noisy and degraded. And what I want to do is I want to train a neural network that's going to try to predict X to the best of its capability. And we're not going to design any type of neural network. We're going to assume that neural network has been trained for minimizing mean square error loss, right? So mean square error loss means I minimize L2 loss between the composition of degraded image and the clean image, right? So that will be the restoration operator. Now, one thing I should mention, and this consistently causes confusion when I talk about this topic, as this S equals HX plus N is not the inverse problem I'm actually trying to solve. Okay, it's a different problem. It's a pretext task just to obtain a formulation for the network, right? It's not matched to the task I'm trying to solve. All right, so few remarks about this, right? As I said, this is not equivalent to deep unfolding or deep equilibrium because my inverse problem I'm trying to solve is not based on H. H is just another restoration problem that I'm training for, but I really want to solve the inverse problem given by A, okay? And this is not plug and play because I'm not training a denoiser. So this is more general restoration operators that where H is not identity, right? In plug and play, I would train just the pure denoiser where H would be identity. Remark 2s are a vast collection of pre-trained restoration models available, right? So you can have super resolution models, block-in painting models, JPEG compression artifact removal models, the blurring models. And in fact, we could leverage all of those models as a way to build regularizers out of pre-trained restoration models. And finally, the remark 3 is that this will require some kind of new statistical interpretation and algorithms that go beyond both plug and play and deep unfolding and deep equilibrium models. And that's what I'm going to really talk to you about. So the first thing I want to say is just mention this basic result that does a generalization of a Tweedy's formula to this setting, right? So I'm going to assume this is a linear degradation operator. And then if I look at the MMSE restoration operator, so which means restoration operator that minimizes the mean square loss that I put here, then I can write that. So I can say that if I write the gradient, so if I look at the function h, which corresponds to the negative log of probability of degraded observation of the image, the gradient of that h with respect to x will simply be h transpose h times x minus, so residual of the input output of that restoration operator. Okay, and if you look more closely here, this PS here is a probability distribution of a degraded observation, which basically corresponds to Px, which is a true prior of the distribution that being used to train the neural network, convolved with the Gaussian kernel evaluated through this H, right? So you can see there's X minus Z here. So this is like a convolution, but the kernel also has this H inside. So if this would be plug and play, this would become in fact identity here, right? So the PS here is in fact related to the PX, so the actual priors that we want to have through a blurring by a Gaussian kernel, right? So this is what's written here, is a Gaussian function. And of course, if I take H to identity and sigma to 0, this PS will be converging to PX because that kernel will become more and more concentrated around the Dirac function. So this will get closer and closer to the actual prior PX. Okay, so let me now reiterate the point. So what I'm trying to say here is that note two things. On the right-hand side, this PS, this distribution is not something I can easily write down a closed form solution, meaning like I don't know PX. It's not very easy to model. It's not very easy to do it, like write it down mathematically. However, the left-hand side is very easy to evaluate. I simply take my neural network, assuming it's MMSE, I pass through the degraded image through it, I take the difference, I apply the H, and by dividing by sigma, I'm going to get the gradient of this right-hand side, which now opens up the whole world of optimization that I can do over this. All right, so now, by the way, any questions on this slide here? If there are any questions, something unclear, I'll be happy to address it here. All right, if there are no questions, let's just go on. So the first framework that I want to talk to is this stochastic deep restoration priors framework. So this is this year's ICML papers that will be presented very soon by Yu-Yang Hu, who will be attending and presenting that work. So if you're attending ICML, this will be a good place to engage with them on this topic. So if I take this formulation, so the sharp tries to reconstruct images. So the goal is to perform the reconstruction where I have G, which is my data fidelity term, could be least squares, could be another type of data fidelity term you want to minimize. And we want to design a regularizer. For the sharp algorithm, the regularizer we propose has this form, right? So we're writing the regularizer as saying I have a negative log of probability of degraded observation, right? PS. And we saw that PS here. So this is exactly this probability degraded observation evaluated at the degraded image, right? And negative log, this is what it gives us. And what we do is we average this, we take expectation over many degradations, right? So you can imagine If this would be like MRI, I consider many degraded measurement operators for MRI. It could be different blur operators. It could be different degradation. So I'm going to call the sharp regularizer, and we can also put a parameter here to regularization parameters that will allow us to balance the strengths of H, right? So this H here, if you spend a second to think about it, has very interesting interpretation. So this regularizer H is promoting solutions whose multiple degraded observations are degradations of natural images. Okay, so what do I want to say? PS represents distribution of degraded observation of natural images, right? So what we're saying is we want to maximize, so we want to promote solutions to inverse problems, right? Whose basically, if I redegrade those solutions, and I evaluate it through PS, they will behave as if they're natural images or degraded versions of natural images. So this has kind of a nice, interesting, real interpretation. And by having a lot of types of degradations, I'm really opening up to really looking at the natural images through different lens by looking at through different H's in this case, right, and corresponding restoration operators. Now, of course, by reusing the result before and doing a little bit of derivations, you can see that now you can write the restoration operator. So if you assume you have MMSE restoration operator trained for all those degradations, then the gradient of this H can be written in this form. Basically, I'm going to now take residual of the input and output of my neural network. So it's degraded input, clean image. I take I apply H, and I'm going to take expectation over many, many degradation operators, right? And the sigma will pop out here too. So this side on the right-hand side, in principle, can be evaluated easily if I can take multiple degradation operators and generate several types of noise, right? So that's kind of the idea of the sharp algorithm. Now, the key here is that although I cannot really evaluate this for all possible degradations, we could design a stochastic algorithm, right? So the stochastic algorithm basically is what sharp is, where I say, well, I want to minimize this loss, so we're going to write some kind of a gradient-based method. I'm going to take a gradient of gx, and now I'm going to do stochastic gradient of this h, okay? So how do we get the stochastic gradient? Well, instead of taking expectation or all possible, we're going to just take one or several degradations at every iteration. I'm going to redegrade the image. I'm going to take the residual, apply the H, and I'm going to get this H hat. I'm going to apply it at the next iteration algorithm. I'm going to change, and I'm going to continue iterate over this, over multiple iterations and going through all possible degradation operators, right? And again, the key point here to note is that the true measurement model, so the inverse problem I'm trying to solve is given by G here. G is actually my data consistency term, which could be the least squares and has that operator A. But H here is really just a prior. It's a regularizer that comes from, that's defined through, implicitly through a set of degradation operators that we can easily evaluate. All right, so turns out this method works pretty well. We did quite an extensive validation this over many, many problems. So here I present the result for MRI reconstruction. By the way, you can find all the details in the paper and the code online, either online now or it will be soon on GitHub. Basically, here we want to solve the, so this is MRI was 4 times undersampling. So uniform means it's a regular undersampled MRI measurement with Cartesian measurements, and 6 times, this is all simulations here. Sigma here refers to different levels of noise. So standard deviation of noise in the K space, so measurement space in MRI. So you can see more and more noise here for 2 different settings of undersampling. And what we're going to do, we're going to use 8 times accelerated MRI prior, right? So what does this mean? This means that our restoration operator here is the one that removes MRI artifacts from 8 times accelerated, so subsampled MRI data. but we apply this model as a prior to solve 4 times and 6 times. Okay, so there's a mismatch. So you can see that we take a mismatched prior and we say, okay, let's just try to apply it or generalize it to a new setting. We're going to generalize it by simply using the sharp framework, where we're going to redegrade at every iteration to match to the way this prior was trained 8 times, right? So, and then here you can see a bunch of results. So there's zero field, which is basic inverse Fourier transform, total variation, plug and play, FISTA, plug and play, ADMM, DRP. So this first paper, deep restoration prior, which doesn't do stochastic version, DPS, which is a diffusion model, and DDS, which is another diffusion model. Both of them are for posterior sampling, but DDS has been an improvement of DPS for by taking into account the forward model more carefully. I mean, you can find the details in the papers. I'll be happy to talk about. And finally, SHARP is the algorithm I presented. You can see it does quite well according to PSNR and SSIM. So improvements could be quite significant depending on the setting, right? In some settings, maybe it's less, right? Here you can see there is an improvement. So the second best algorithm is always highlighted in blue, and then the best one here is highlighted in red. So let me also show you some visual results. So here you have a ground truth. So 4 times, this is a different setting. So we do have random subsampling. In the paper, you can find more results, by the way. 6 times random subsampling. So you can see PNP, ADMM, DPS, DDS. So both of those are diffusion models, state-of-the-art diffusion models. Then you can see SHARP here, and then finally ground truth. And you can see that SHARP does pretty well. So reusing MRI reconstruction operators for as a prior does much better than using denoisers in all those 3 settings. One deep question is, why can using restoration operators do better than denoisers? One hypothesis we have that we've been working to try to explain better and validate is that if you train an image denoiser, that neural network has been trained to remove additive white Gaussian noise, but it hasn't been trained to address other types of artifacts, which could lead to suboptimal. So there's a mismatch when you apply a denoiser at every iteration of an iterative algorithm to the tasks that the denoiser is trying to solve, or it's been trained on, to the task you're trying to solve, right? So in some sense, the framework of using restoration operators tries to bridge this gap. So although it's not the same artifact it's been trained on, it's still been trained on MRI restoration in this case, right? So it's kind of has seen similar type of down sampling artifacts. All right, the key advantage though, so while we can use this in a prior, one of the key advantages of using restoration operators is that they can be directly trained on noisy and subsample data. And here I cite the 2 papers if you want more details about this. In particular, this 2023 paper gives the theoretical result that I'm going to present to you today. So if I would have a fully sampled, so to train a denoiser, I would need a fully sampled image X, in the case of MRI, right? Ground truth image. I will need to add additive white Gaussian noise to it to train it. And finally, once I train it, I will end up with a regularizer that's going to be based on the denoiser. However, in some settings, in particular in MRI under motion, right, for free-breathing MRI, we don't have access to the ground truth image. So only thing we can have access to are subsampled measurements, right? So what you see here is a subsampled K-space where it takes every 8th line, right? You can see it skips 7 and takes 8, and then skips 7 and takes 8. So instead of having this, we only have this, right? But the key is, it might be much easier to have 2 subsampled measurements instead of 1 fully sampled. So if this is skipping every 7 here, this one is also 8 times subsampled, but skipping in a different way, right? So both of those are 8 times accelerated MRI measurements, which means if I put them together, I still don't get fully sampled K-space, but each one is complementary to each other, right? So if I take this image, so you can see this H here, the Fourier transform, M is a subsampling. If I bring it back to image space, I'm going to get this artifact corrupted image. So now I could train a neural network to restore it. How do we do it? We pass it through the CNN. It gives me output. And what I'm going to do is I'm going to minimize the gap between the redegraded version of this image, right? I take this reconstructed image outside, I redegrade it to match my second measurement, so I have pairs of measurement, and I try to minimize mean square error, and this is a weighted loss. So this is a self-supervised loss. So that's why I put this here, L, self-supervised. Note that it never needs any X directly. Only thing it needs is two subsampled measurements, S prime and S. So given pairs of subsampled measurements for each image, for each object, we can easily minimize this loss to get back. And note that this, finally, this R theta that we're training is just a restoration operator that's taking this image here and trying to restore it by removing those artifacts. So the key thing here is that if I assume that masks, meaning measurement masks, images, and noise are all sampled independently or distributed independently from each other, and that if I take expectation over all possible subsampling masks across the data set, that should be identity. So which means for each image, it is still subsampled. But if I look across all images and I would put together all the masks, then I would cover the whole space Rn. Then you can show that this loss that we use for self-supervised is exactly the supervised restoration mask, restoration loss, which basically means we can train the restoration network without any clean ground truth data by simply using pairs of the measurements, degraded measurements. So this is very much related to the idea that was originally presented by noise to noise for image denoising. The difference here is that we don't only consider noise, we're looking at the degraded version of the images by putting this forward operator. But now, a nice thing about this, I can take this restoration operator and directly plug into Sharp to use it at test time, right? And here are some results. So you can take this thing, plug it into Sharp, and here we put a bunch of other results. So ADMMTV, graph, Spicer, also the methods that don't need any fully sampled data in different settings. And PNP ADMM is highlighted because that uses a denoiser that's been trained with fully sampled data. All right, and finally, I'm coming to the 37 minutes. I'm trying to keep this talk like around 40 minutes or so. Let me just mention another angle to generalizing this idea of looking at fixed point restoration operators, and this is collaborations with Matteo Terris and Toma Moro. We could, in this work, we try to say, okay, let's try to come up with another form of regularizers that could give other types of properties. And in particular, we're going to define the regularizer H as the function that minimizes the distance to the set of degraded restored pairs, right? As I said in the beginning, the premise of this talk is that the fixed points of degraded restored composition will look like natural images. So in here, we're trying to explicitly say we want to minimize the distance to fixed points of degraded restored images, right? And we're going to do it by over all possible pairs of degradations and restorations. And of course, restoration and degradation are matched. So it's the same epsilon here, right? And basically, we're trying to minimize distance to those fixed points. And we're going to define this function H, put some regularization parameter, and we called it FIRE, so fixed points of restoration, all right? So now, the nice thing is, if the concatenation of degradation and restoration is a projection onto a closed prox regular set, then it's quite known that the gradient of this term inside the expectation will simply be the residual of degradation and restoration, right? Very similar to the sharp there, but no, there's no H anymore in front of it, right? It's simply the residual of this thing, right? And basically, we can now design another algorithm. So unlike sharp, we're not going to have H transpose H here, but we're going to still have the residual of the graded restored composition and the input image. And this is going to be the stochastic gradient of this regularizer. And we can just run this any your favor optimization algorithm. It could be gradient descent. In this paper, we used half quadratic splitting, but you could use any other method as well to do the optimization. And what we did is we picked basically very different types of degradation restoration. By the way, the whole framework is compatible with denoising as well. If you set H2 identity. So we looked at denoising, super resolution, the blurring, and by using multiple restoration priors as a stochastic way, we could obtain really excellent results across multiple problems, motion blur, Gaussian blur, super resolution, and so on. So basically, FIRE using multiple very distinct restoration models achieves state-of-the-art performance on multiple tasks. I'm not going to spend too much time here. You can see here's DPIR, state-of-the-art plug and play. DRP is a paper from iClear, and DiffPeer is a diffusion model. Anybody interested, I invite you to look at the paper, ask me questions. I'll be happy to talk about it. And basically, I want to wrap up my talk at this moment with what I talked. So basically, to summarize all my talk, my focus has been on using restoration priors that are more general than the noisers, but as regularizer for solving other types of inverse problems, right? And the good thing is there are many of those kind of models available nowadays. But the second thing I wanted to say is one of the key benefits of using restoration priors is that they can be trained very often without ground truth if you have pairs of degraded observations, right? And both SHARP and FIRE provide two different algorithmic frameworks. They could allow you to integrate those restoration priors to try to address inverse problems. And just to wrap it up, I want to thank my team at WashU for doing this work. If anybody here interested in this topic, feel free to reach out and talk to me. Every year we recruit PhD students, and most likely we'll be recruiting a postdoc next year. Please feel free to reach out. And thank you everyone for listening, and I'm open for questions.